Welcome back. We're going to pick up from where we stopped off in the first section of this video. We were examining how to run logistic regression. We did one with a single predictor in the model. Specifically, we were working with a data set of credit cards, and we used age to predict whether somebody signs up for a credit card or not. We're going to expand that model now to a multiple logistic regression context. We're going to examine the role of age, income, and home value on somebody's likelihood of signing up for a credit card. So to get started, let's run the model. We're going to go over to SPSS and load up our model. So we're going to go over to Analyze, Regression, Binary Logistic. We're going to add on two more variables to what we had before. We had before just age. Now we're going to bring in income and home value into this model. Therefore, we're examining the effects of age, income, and home value on somebody's likelihood of accepting a credit card offer. All right, let's start interpreting the output now. As was the case for the previous example, we're going to examine this in two sections. We'll first examine prediction and then discuss inference. Under prediction, we'll focus here on the initial output in front of us. We have a total of 1,000 observations that are analyzed in this data set. We're predicting whether somebody signs up for a card or not. That's a yes or a no. Yes, indicating they did sign up for a card. Now, block 0 is going to be the same for this model as it was for the previous model. You'll recall block 0 is one where it's a baseline model. It's a model that is based on not using any predictors. So all you have is your outcome variable, and predictions are typically made based on majority class. In this case, if given the option between predicting whether somebody signs up for a card or doesn't sign up for a card, since most people in our sample don't sign up for a credit card, if we had gone with the majority class prediction, our accuracy would have been 52.4%. That sets a baseline for what we want our accuracy to be, in any other model. That's sort of like the lower bound. So moving along, let's go to block 1, which is what is really going to tell us how well our model is performing. So the first criterion we're going to look at here is the extent to which the -2 log likelihood for block 1, that is our model, is better than a similar metric for block 0. It turns out for block 1, our -2 log likelihood comes to be 1132. This number is lower than the one for block 0. And I don't know exactly what the number for block 0 is because, again, SPSS doesn't give us that number. But we can see out here what's important is the difference between block 0 and block 1, indicated by the model chi-squared, is 251.009. This number is significantly different from 0, telling us that block 1 model is significantly better than the one in block 0. We can go on now that we know that the model is better than no model. We can go on to examine performance metrics or quality metrics, how good our model is. We're going to look at two such metrics. One of them is our set of pseudo R-squares. So we have here Cox and Snell R-squared and Nagle-Clark R-squared. These indicate to us how good the model is. Bigger the R-squared, obviously, the better the model. We use the same heuristics you would use for linear regression, interpreting these pseudo R-squareds. So 0.1 to 0.5 reflects a moderate strength model, and that's what we have here based on either Cox and Snell or Nagle-Clark R-squared metric. Moving along, let's examine our classification table. But before we examine this classification table, let's go through some background about the source of the numbers in the classification table. So the numbers in the classification table are derived from our predictions. Specifically, you'll see a column called pre2, which contains predictions of, or the predicted probability of a person signing up for a card. Now, when you translate that to either somebody signing up or not signing up, you'd say, using a default 0.5 threshold, the prediction would be, yes, they would sign up. Now, if you were to the third person, yes and yes, that was a correct prediction. And the fourth person, again, likewise was correct. For the fifth person, a correct prediction. Sixth person, again, correct. And seventh person, we were wrong about. Going on to the eighth person, we've got here a correct prediction. And the ninth person, again, we are right about predicting that. And then the 10th one, we are, again, correct. So you can look at these numbers here and kind of arrive at the conclusion that out of 10, we've got 7 correct. And therefore, the accuracy would be 70%. Now, in the same manner as we just went over, imagine combining or doing this for all the data. Well, that's what the classification table contains. The classification table summarizes combinations of contains combinations of what's an offer and PGR2. So for instance, you've got a no yes that's highlighted right now on screen. You've got a yes no highlighted below that. So you count how many times yes and no occurs, how many times yes and yes occur, how many times no and no occur. You would then get counts essentially of how frequently each one of these combinations occur. Obviously, the times when PGR2 and offer match up are correct predictions. The ones where they don't match up are incorrect predictions. Let's go and look at our summary table then that summarizes all this, raw data. So our summary table contains here a summary that tells us we have 412 of our respondents that we predicted would not sign up for a card and did not sign up for a card. Similarly, the 316 we predicted would sign up for a card and did in fact sign up for a card. There were 112 that we predicted would sign up for a card, but in reality didn't. Similarly, the 160 we predicted would not sign up for a card, but did. So the circled numbers are incorrect predictions. The ones in rectangles are correct predictions. So 412 plus 316 gives us 728, which divided by 1,000 gives us 72.8%. The accuracy of our model is 72.8%. It is worth noting here that the classification of what qualifies as a yes or no for prediction is based on a cut value of 0.5. More specifically, if our predicted probability was 0.7, we would predict that person as being a yes, and 0.4 as a no. Okay. So that completes the prediction part of our model. Let's move it looking at the inference part of our model. Now, if you in this output, you can look at your individual regression coefficients and arrive at the conclusion that each one of them is statistically significant. That is, income, home value, age, all three of them, let me fix that box, all three of them exert a significant influence on the likelihood of somebody signing up for a credit card. So our equation as such would look something like this then. It's messy looking. natural log of p divided by 1 minus p equal to minus 4.417 plus 0.13 times age plus plus 0.003 times home. That's our equation then of the logistic regression model. Moving along, a common, we frequently want to also interpret the meanings of the individual variables from logistic regression. One way to do that is to take the individual variables coefficients and draw inferences from that. In linear regression, you can draw inferences directly from the raw unstandardized regression coefficients. Unfortunately, in logistic regression, because our outcome variable has been transformed, we need to then convert our variables back to regular units from log units. One way of doing that is to exponentiate the regression coefficients. Exponentiation negates the effect of a log function. Here, the way we interpret these exponentiated regression coefficients is as follows. We compare this number to 1 and multiply it by 100. What that gives us then is, it'll give us the likelihood of, or rather, it will tell us that when age goes up by 1 year, the likelihood of signing up for a credit card goes up by 1.3%. Similarly, you could take the number for household income and draw the following inference. As income goes up by 1 unit, likelihood of signing up a credit card goes up by 3.2%. To be more clear out here, when income goes up by 1 unit, meaning $1,000, likelihood of signing up for a card goes up by 3.2%. Furthermore, when home value goes up by $1,000, likelihood of signing up for a card goes up by 0.3%. That is 1.003 minus 1 times 100 is 0.3%. Okay. This is how you interpret the regression coefficients in a multiple logistic regression equation. Okay, that sums up how you would interpret a simple logistic regression equation then onto a multiple logistic regression equation. The one thing that does remain is interpreting strength of variables. When you've got many variables, you commonly want to examine which is the strongest predictor. Now, we already know that you can't look at the unstandardized coefficients to draw this comparison. You've got to look at a standardized kind of variable, and in logistic regression, that is the wall statistic. The wall statistic tells you which of the predictors has the, is most important and most predictive of the likelihood of signing up for a credit card. It turns out in our data, the most predictive would be, or most important would be income, followed by home value, followed by age. These again reflect the relative importance of these predictors in influencing the outcome variable. All right, so let's get back to our example here. Now, what we're going to now examine here is, the last thing we're going to do here is we're going to examine the effect of changing the classification cutoff and what that means. So let's go back to our data and see the effect of changing the classification cutoff. So you'll notice out here, we have numbers like 0.71 that got classified as yes, 0.2 as no. These are based on a default classification cutoff of 0.5. Let's look for that in our menus. If you click on options, there's an option here for the classification cutoff. By default is 0.5. We're going to make that now 0.3 and see the effect of that. Okay. So when you change the classification cutoff, you get different categorizations of the predicted probability. Specifically, you'll notice while we'll look for an aberrant example. Okay, here is one. For the fifth observation, our data, when we had pre-2 and pre-3 are the same, the predicted probability is the same. The translation of predicted probabilities is going to be different because our classification cutoff has been changed. So in the previous example, when we were using a cutoff of 0.5, 0.34 got classified as a no. Now, because our cutoff is 0.3, 0.34 gets classified as yes. Now, this change has no impact whatsoever on the statistical results. Specifically, you're going to find the same numbers for model chi-squared, Cox-Cell R-squared, and even the variable coefficients are going to be the same. The only thing that you'll see changing is the classification table. Notice in the classification table now we have different numbers along the diagonal. These, of course, are the correct predictions. That gives us an accuracy of 64.3%. Now, 64.3% is hard to judge whether it's good or bad. Let's look at our baseline. Our baseline here is 47.6%. Yeah, using that cut value. So compared to our baseline, you'd say we're doing better than our baseline. But that's you know, we do know that from our previous model, our classification table there yielded us a 72.8%. So changing that cutoff value, the cut value, can have an effect on your accuracy values, but it won't affect any of the statistics like the -2 log likelihood or the model chi-squared or the R-squared values. They'd all be unchanged. So would the regression coefficients be unchanged. The accuracy number, however, is important, and many folks will equate the classification cutoff to a measure of risk. So in a sense, if you are lowering the classification cutoff, you're making it more likely that you make predictions that are 1. So by dialing that cutoff down or up, depending on what your outcome variable is, you might be affecting the level of risk you're willing to take or interested in taking. Okay. Now let's take a look at one more example where we can put it all together. We're going to look at an example of some data from Titanic, the ill-fated Titanic ship. Now, bear in mind, you know, my main goal here is to kind of highlight again the interpretation of coefficients. So we'll look at the Titanic data to again put all these things together. So coming up in front of you now is data on Titanic. So here's some data on the ill-fated Titanic. In this data set, we're predicting whether somebody survived aboard the Titanic or not, using some variables about the folks on board. We'll keep it simple here by picking out just a few of these variables here. We want to again predict survival aboard the Titanic, a binary outcome, based on the gender of the passenger, their age, number of siblings or spouses on board, number of parents or children on board, and the amount they paid for their ticket in 2014 prices. Okay, let's run this thing. So we're going to go survive goes to dependent variable. We'll move people's sex, age, sibling spouses, parents and relatives, and passenger for 2014 over to the right. We'll use a numeric version of gender rather than a string version of it. So just so we know here, sex numeric is such that male is 1, female is 2. This is important to note here. Okay, so female is 2, male is 1. Okay, so let's take a look at our output and make sense of the results we have. Our data has 891 observations, of which only 714 are complete. We have coding of no and yes for survival. Yes means it survived. No means 0 means they didn't survive. Most people didn't survive. So if you made a prediction that nobody survived, your accuracy would have been 59.4%. We'll focus here on block 1, which is the crux of what we're looking for. In block 1, we first examine the model chi-squared, which tells us whether our model is better than not having one. Since the model chi-squared is less than 0.05, we can safely conclude that our model is better than not having one. We can also see here our R-squared numbers are in the moderate range, 0.1 to 0.5. And lastly, our classification table shows us a 77.9% accuracy, okay, which is better than what we had for in block 0 of about 59%. So in all three metrics, our model is performing better than a random guess. Let's go on to the part about inference now and make sense of those results. What we have here is we have a couple of variables. Let's examine them one by one. Some of these are significant. These are age is significant, sibling spouse is significant, number of parents, children is significant, passenger fares, gender. All the variables are statistically significant because they are below 0.05. Okay, let's move along to look at strength of effect. In terms of strength of effect, the strongest variable here strongest predictor is, let's get this, is gender, followed by passenger fare, followed by siblings and spouses on board, age, and then finally number of parents and children on board. Okay. Next, we're going to go in and look at interpreting individual coefficients. Let's begin by interpreting passenger fare to see what that means. Let's go with age. So age is significant, so we can interpret this coefficient. What you can learn from this particular output is that when age goes up by 1 year, the likelihood of surviving changes by 0.979 minus 1 times 100 is equal to 2.1%. In other words, or minus 1%. In other words, older people had a much lower chance of surviving aboard the ill-fated Titanic. The likelihood of surviving aboard the Titanic declined by 2.1% with every passing year. Somebody 1 year older had a 2.1% less chance of surviving. Similarly, let's try and interpret here the coefficient of gender. Gender is a particularly interesting one here because the variable is categorical. So we have here two levels of gender, and they're female and male. And the numbers denoting the two levels are 2 and 1 respectively. Female is 2, male is 1. So an increase in the value of sex numeric would indicate a comparison of female to male. Okay, higher the number, female, lower number, male. So if you were to compare males to females, that is what happens to likelihood of surviving after sex numeric goes up by 1, well, the likelihood of surviving of females compared to males is 12.596 minus 1 times 100, or 1159.6% higher. So females have a 1159.6% higher chance of surviving aboard the Titanic than do males. Again, bear in mind this interpretation is based on the knowledge or knowing that sex numeric is coded as 1 and 2, where 2 is female, 1 is male. Alrighty. So we've gone over here the basics of logistic regression, the mechanics of logistic regression, and then we went on to examine the prediction and inference goals of logistic regression. We conducted logistic regression with a credit card data set and then on to a data set on Titanic survivors to, to see how to interpret a logistic regression output. Right? Thank you so much for joining me.